Did you know this? For more than 70 years, humanity has spent billions of dollars staring at distant galaxies, billions of light years away. We have photographed dying stars at the very edge of the universe. We have searched for echoes of the Big Bang. We have mapped hundreds of millions of galaxies. And yet, all that time, we somehow overlooked the star closest to Earth. A star that, on a clear night, you can see with your own eyes just by looking up from your home. A star only 4.5 light years away, which in cosmic terms makes it practically our next-door neighbor. It wasn't because scientists didn't want to study it. It was simply because they couldn't. Its light was too bright, too close, overwhelming everything around it, like headlights shining straight into your eyes in the dark. Until December 2023. That was when the James Webb Space Telescope, humanity's $10 billion machine, turned its gaze toward Alpha Centauri. What it saw over just 3 days of observation left the scientific community stunned into silence. They found something every theory said should not exist. Something textbooks insisted had vanished billions of years ago. And yet there it was. Alive. Active. This is the story of a discovery that could completely change how we see the universe. A story about a mysterious world hiding right in humanity's own backyard. Alpha Centauri. The name sounds distant and unfamiliar, but in reality, this is the closest star system to Earth in the vast universe. Just 4.37 light-years away. It still sounds far, sure, but on a cosmic scale, that is basically the distance between your house and your neighbors. With something that close, you would think scientists must have studied it inside and out, right? They should already know everything about it, from the temperature of its surface to the planets orbiting around it. But the truth is exactly the opposite. For nearly 70 years, Alpha Centauri has been almost a blind spot on humanity's map of the universe. Not because scientists didn't care, but because it was too close, too bright, to the point of being impossible to study. That sounds ridiculous, doesn't it? How could something nearby be harder to observe than something far away? To understand this, imagine standing right next to a car's headlights while they're on. Now try to spot a firefly flying nearby. You won't see anything except a blinding glare that makes your eyes sting. That is exactly the problem with Alpha Centauri. Its light is so intense that it drowns out everything around it. Any planets that might exist there are completely swallowed by that glare. We simply cannot tell where the star ends and a planet begins. Scientists call this the paradox of proximity. The thing you expect to be the easiest to observe becomes the hardest. Like being able to take a sharp photo of a building across the city, but failing to photograph the tree right in front of you because it's too close to the lens. In 1990, when the Hubble Space Telescope was launched into orbit, the entire world was excited. This was the most powerful observational machine humanity had ever built. It could see galaxies billions of light years away. It could capture light from stars being born, or stars in their final moments. Scientists believed that with Hubble, they could finally study Alpha Centauri in detail. They pointed its lens toward the system, full of hope. Then they realized they were wrong. Hubble, powerful as it was completely helpless against Alpha Centauri. The star's light was still too bright, still overwhelming everything around it. Like owning the most expensive telescope on Earth and still being unable to see a firefly next to a headlight. The tool wasn't the problem. The nature of light was. Ground-based telescopes were even worse. Not only did they have to deal with Alpha Centauri's glare, but also with Earth's atmosphere itself. The air around us is constantly moving, constantly shifting, turning images from space into blurry smears. You can see this effect when you look at stars at night. They don't stay still, they flicker and shimmer. That's the atmosphere distorting their light. And then there was another complication. Alpha Centauri isn't a single star. It's a system of 3 stars orbiting one another. There is Alpha Centauri A, the main star, slightly larger than our Sun. Alpha Centauri B, a bit smaller, orbiting A in a wide path. And far beyond them both is Proxima Centauri, a small red dwarf star. These three stars pull on each other through gravity, creating a complex cosmic dance. Their gravitational forces don't just affect each other, but everything around them. Any planet trying to exist in this environment would be tugged from three different directions. Its orbit would become chaotic, unpredictable. Scientists tried anyway. They spent years developing new techniques, new methods to filter light and analyze data. But every time, they hit the same wall. The technology of the time simply wasn't powerful enough. Gradually, the scientific community accepted reality. Alpha Centauri, despite being only a few light-years away, would remain a mystery, at least for the foreseeable future. They turned their attention to other targets, places much farther away, yet easier to observe. It was ironic, wasn't it? We could clearly see a galaxy billions of light-years away, but we couldn't see a planet, if one existed, orbiting the nearest star. We could study black holes at the edge of the universe, but knew almost nothing about our own neighbor. Generations of scientists came and went. The 1990s turned into the 2000s. Then the 2010s. Then the 2020s. Alpha Centauri was still there, blazing in the night sky, so close it felt like you could almost reach out and touch it. Yet its secrets remained hidden. At scientific conferences, Alpha Centauri would occasionally come up. "We need new technology," they would say. "We need a completely different kind of telescope. A machine capable of blocking out the star's light to see what's hiding behind it." The idea sounded crazy. Build a machine that could block the light of a star. How could that even be possible? The cost would be astronomical. The required technology didn't even exist yet. And then, in the early 2000s, a project began to take shape. The most ambitious project in the history of space science. They called it the James Webb Space Telescope. At first, this project wasn't aimed at Alpha Centauri at all. Its main goal was to look deep into the universe's past, to capture light from the first stars formed after the Big Bang. But during the design process, engineers realized something. With the technologies they were developing, maybe, just maybe, they could finally look at Alpha Centauri too. The cost kept rising. From $1 billion to $3 billion, then 5, then 10. The launch date kept slipping. 2010, no, 2015. No, 2018. Then 2020. Many people began to doubt. Would this machine ever make it into space? Would it really work as promised? Until December 25, 2021. From a launch site in French Guiana, an Ariane 5 rocket lifted off, carrying humanity's $10 billion machine. The James Webb Space Telescope, after 30 years of development and countless delays, was finally on its way to space. Its destination was not Earth orbit like Hubble's. It would travel much farther, to a point known as L2, about 1.5 million kilometers away from Earth, on the far side of the Sun. There, Webb would remain in constant shadow, shielded from the Sun's heat and light, allowing it to detect the faintest signals from deep space. It took 6 months for Webb to fully deploy its instruments, to test and calibrate them. Then it began its work. The first images it sent back stunned the world. Distant galaxies revealed in breathtaking detail. Clouds of gas giving birth to new stars. Giant planets hundreds of light-years away. Everything was beautiful. Everything was scientifically invaluable. But in December 2023, Webb received a different assignment. One that no one truly believed would succeed. Turn toward Alpha Centauri. To understand why James Webb can do what Hubble never could, we need to talk about how they see the universe. Hubble sees invisible light, the exact same kind of light your eyes are using to read these words right now. That's why Hubble's images look so stunning, filled with rich, vibrant colors. It captures light the same way our eyes see the world. James Webb is completely different. It doesn't see invisible light. It sees in heat. Did you know that everything gives off heat? Your body is releasing heat right now. So is the phone in your hand. The table, the chair, even a cold concrete wall, all of them emit a special kind of light called infrared. Human eyes can't see it, but you can feel it when you place your hand near something warm. That is exactly what Webb uses to observe the universe. Instead of capturing visible light, it detects thermal radiation. It's like not looking at a candle's flame, but feeling the warmth spreading from it. Why does this matter for Alpha Centauri? Because when you look in visible light, the main star overwhelms everything around it with its brightness. But when you look in heat, things become clearer. The star is still hot, still radiating energy, but now you can also distinguish smaller heat sources around it, planets, clouds of dust, other objects radiating their own warmth. Think of it like this. You're standing in a dark room. Someone shines a powerful flashlight straight into your eyes. You can't see anything except that blinding glare. Now instead of trying to see with your eyes, you close them and sense the temperature around you. Suddenly, you can see that someone is standing next to the flashlight because their body gives off heat. You can see a refrigerator in the corner because it's colder than the room. The blinding light no longer matters. That's exactly how Webb works. The intense glare from Alpha Centauri can't hide the heat sources around it anymore. For the first time, we can see into regions near the star that were previously complete blind spots. But for Webb to do this, it has to be kept unbelievably cold. Extremely cold. -233 degrees Celsius. Colder than outer space itself. Because Webb also gives off heat. If it were warm, its own thermal glow would drown out the faint signals coming from the deep universe. That's why Webb has a massive sun shield, about the size of a tennis court. The shield always faces the sun, blocking nearly all sunlight and heat. Behind it, the instruments sit in permanent darkness, frozen and silent. Even so, seeing in heat alone still isn't enough. Because bright or not, Alpha Centauri is still a massive source of heat. Its thermal radiation is strong enough to overwhelm everything nearby. This is where Webb's second piece of technology comes in, something with a strange name, the coronagraph. The word comes from corona, the glowing halo around the sun that you can only see during a total solar eclipse. When the moon completely blocks the sun, what's hidden behind the glare suddenly appears, that faint halo, the streams of hot plasma rising from the sun's surface. A coronagraph does the same thing, but artificially. It creates a fake eclipse inside the telescope. Deep inside Webb, there is a tiny mask placed precisely where a star's light comes into focus. When Webb points at Alpha Centauri, the star's light races straight into the telescope. But before it reaches the detector, that tiny mask blocks it completely, just like the moon blocking the sun during an eclipse. The result? The main star vanishes from the image. All that remains are the objects around it, things that were once completely hidden. It sounds simple, but in reality it's incredibly difficult. The mask has to be manufactured with precision down to fractions of a millionth of a meter. It has to be positioned perfectly, without being off by even a hair's width. Because starlight isn't a perfect point, it scatters, it ripples, it creates glowing rings around the center. Engineers spent decades refining this technology. They tested countless designs. They calculated every angle, every curve. Because even the slightest error would let starlight leak through and ruin the entire image. In the end, they succeeded. Webb's coronagraph is the most precise device ever built for this purpose. It can block a star's light with near-perfect accuracy, revealing faint objects around it, objects millions of times dimmer than the star itself. By combining these two technologies, Webb's ability to see heat and its coronagraph that blocks starlight, humanity finally gained a tool powerful enough to look at Alpha Centauri. Not just glance past it, but truly see what's there. For 70 years, it was like standing in front of a thick curtain. We knew something was behind it. We guessed. We hoped. We built theories. But we never really knew for sure. Now, for the first time, that curtain was about to be pulled aside. December 2023. Scientists at the Space Telescope Science Institute in Baltimore received the observing schedule. Webb would spend 3 days pointed at Alpha Centauri. 3 days doesn't sound like much, but for a telescope as valuable as Webb, booked solid with hundreds of competing projects, 3 days was a major investment. Their expectations? Honestly, not very high. Maybe they'd see a few rocky planets. Maybe just dust. Or maybe nothing at all. Most scientists treated this as a test, a chance to see whether Webb could really block starlight as effectively as designed. No one expected they were about to witness one of the most shocking discoveries in scientific history. On the first day of observations, data began streaming back to Earth. It took hours for the radio signals to cross the 1.5 million kilometers between Webb and Earth's receiving antennas. Then the data was processed, analyzed, transformed into images. When the first images appeared on the screen, the room fell silent. Not the silence of disappointment. The silence of shock. They were seeing something. Something unmistakable. Something far beyond anything they had predicted. One scientist checked the instruments. Could this be a malfunction? Another started calling colleagues. You need to see this. Right now. On the second day, more data poured in. Every hour added clarity, detail, confirmation. What they were seeing wasn't an error. It wasn't noise. It was real. By the third day, they knew for certain they were looking at something theory said should not exist. Proxima Centauri b, the planet orbiting the small red dwarf star in the Alpha Centauri system, was not just a dead, lifeless rock as everyone had assumed. It had an atmosphere. A real atmosphere. Thick. Structured. That might not sound especially dramatic to you. But to scientists it was almost impossible. Because they knew what Proxima Centauri is like, the star this planet orbits. And Proxima Centauri is a monster. Early in the morning of December 15, 2023, at the Space Telescope Science Institute in Baltimore, a group of scientists gathered in the control room. They sipped coffee, made small talk, and prepared for an observation run that most of them assumed would be uneventful. Webb was about to turn its gaze toward Alpha Centauri. 3 days of observations were scheduled. But no one truly expected anything extraordinary. We might see a few rocky planets, someone had said in an earlier meeting. Maybe just dust clouds. Or possibly nothing at all. That attitude was not pessimism. It was simply the mindset of scientists, people who had hoped too much before and been disappointed too many times. They had learned not to set high expectations for early observations, especially when the target was something as difficult as Alpha Centauri. In fact, most of them treated this as a technical test. They wanted to see whether Webb's coronagraph really worked as intended. They wanted to know if its starlight blocking technology was powerful enough to reveal faint objects nearby. Alpha Centauri itself was just a test case. Some even placed casual bets. $5 says we see nothing but noise, a young engineer joked. Others laughed. They were used to this, spending months preparing an observation only to receive meaningless data. Still, they had to try. Because there was always a tiny chance, 1%, maybe 1 in 1,000, that they might find something interesting. That is how science works. You never know the outcome until you actually look. At 8 a.m. local time, Webb began executing its commands. From a distance of 1.5 million kilometers, the massive machine slowly rotated, aligning itself with pre-programmed coordinates. Instruments powered on. The coronagraph activated. Webb was now looking toward Alpha Centauri. The first hour passed in relative calm. Data from Webb did not arrive instantly. Radio signals needed time to cross the vast distance between the telescope and Earth's antennas. Then the data had to be processed through multiple layers of computers, filtered for noise, and converted from raw numbers into images humans could see. The scientists went about their usual routines. Checking email. Drafting reports. One person stepped out to buy sandwiches for the group. Waiting was part of the job. But when the first images began appearing on the screens, the mood in the room shifted. The data processing lead, a scientist named Sarah who had worked with Webb since its earliest days, frowned at her display. She checked the parameters. Then checked them again. "Hey," she said quietly. "Can everyone take a look at this?" Her voice was not loud, but something in her tone made people stop. Coffee cups were set down. Chairs pushed back. Slowly, they gathered around Sarah's screen. "This is from Proxima," she said, pointing to a faint streak of light. "Planet B. We've known it existed since 2016. Heads nodded. Proxima Centauri b was the first planet discovered in the Alpha Centauri system, found through indirect methods by measuring the tiny wobble of the star as the planet tugged on it gravitationally. But no one had ever truly seen it before. "So what's the issue?" someone asked. Sarah zoomed in. "Look at this spectrum." A graph filled the screen, colored lines rising and falling like waves. To an untrained eye, it looked like meaningless noise. To these scientists, every line told a story. They were chemical fingerprints. When starlight passes through a planet's atmosphere, certain wavelengths are absorbed by gases in that atmosphere. By analyzing which wavelengths are missing, scientists can determine what the atmosphere contains. "I'm seeing signatures of water vapor," Sarah said slowly. "Clear as day. No ambiguity." The room fell silent. Water vapor alone was not unheard of. Many gas giants have water in their atmospheres. "But this isn't a gas planet," someone else said. "Proxima b is rocky. Roughly Earth-sized." Sarah nodded. "Exactly. Which means it has an atmosphere," another voice finished the thought. "A real atmosphere." Silence returned, heavier this time. Not the comfortable kind, but the kind filled with disbelief and excitement. Because this should not have been possible. Proxima Centauri, the star this planet orbits, is a red dwarf. These stars are notorious for violent energy outbursts called flares, powerful enough to strip the atmosphere from any planet orbiting too close. The theory was clear. A small planet like Proxima b, orbiting an active red dwarf, could not hold on to an atmosphere. Its gravity was too weak. The radiation too intense. Any atmosphere it once had should have been blasted away billions of years ago. And yet, Webb was showing them the opposite. "It could be an error," someone suggested. "We should rerun the data processing." Sarah nodded. "Already doing it." The second hour passed in tension. No one returned to their individual work. All eyes stayed on the screen, waiting for the second pass. Meanwhile, new data continued streaming in from Webb. Each additional minute brought more information. Images sharpened. Spectral graphs grew more detailed. The second processing run finished. Identical to the first. No errors. The water vapor signal was still there, unmistakable. "Check the instruments," someone said. Maybe Webb is misreading. But deep down, they knew Webb was not wrong. The telescope had been tested exhaustively. It had observed hundreds of other targets with flawless results. There was no reason for it to fail now. "Wait," Sarah said suddenly. She zoomed into another section of the spectrum. "Look at this." New lines appeared on the screen. Signatures of other elements. "Is that oxygen?" someone asked, their voice trembling. "It looks like it," Sarah replied, though she sounded unsure herself. "That can't be right," another person said. "We need to verify this." The third hour began. No one left the room. Lunch was forgotten. Phones rang and went unanswered. Sarah called a colleague at another institute, a planetary spectroscopy expert. "You need to see this," she said. "Right now. I'm emailing the files." While waiting, the team kept analyzing. They ran every possible check. Compared the data with previous observations of other planets. Looked for any conceivable source of error. But the more they checked, the more certain they became. This was not a mistake. This was real data. Proxima Centauri b had an atmosphere. That atmosphere contained water vapor. Possibly oxygen. Things theory said should not exist. The colleague called back. "Is this data real?" he asked, skeptical. "We've verified it 3 times, Sarah said. Then, he paused. "Then we need to call an emergency meeting. Now." Over the next few hours, the news rippled through the scientific community like a shockwave. Emails were sent. Phone calls made. Leading exoplanet scientists were alerted. By the end of the first day, one thing was clear. They were seeing something completely outside all expectations, something no theoretical model had predicted. But this was only day 1. Webb still had 2 more days scheduled. No one expected what would be revealed next to be even more shocking. That night, few of the scientists slept. They lay awake, replaying the data in their minds, searching for explanations, wondering if they had missed something. But the next morning, as data from day 2 began arriving, all doubt faded. There was not just an atmosphere. It had structure. Distinct layers. Signs of winds, of weather, of complex dynamic processes. "This isn't a dead rock with a thin veil of gas," Sarah whispered as she studied the new data. "This is an active world." The word active made everyone pause. Not alive in the biological sense, but alive in the sense of motion, change, and evolution. Like Earth. The biggest question was no longer what is there, but how it could possibly exist. Because according to everything they knew, Proxima b should have no atmosphere, no water vapor, nothing but a bare rocky surface scorched by its parent star's radiation. And yet there it was. Dynamic. Defiant. Challenging every rule humanity thought it understood about the universe. Proxima Centauri b. The name is no stranger to the scientific community. Astronomers have known about its existence since 2016, nearly a decade ago. Back then, no one actually saw the planet. It was discovered indirectly, by watching its star, Proxima Centauri. When a planet orbits a star, its gravity tugs ever so slightly on the star, making it wobble, like a dancer shifting their weight. By measuring these tiny motions, scientists were able to calculate that a planet had to be there. They worked out its mass, about 1.2 times that of Earth. They calculated its distance from its star, roughly 7.5 million kilometers, far closer than Earth is to the Sun. They figured out its orbital period, 11.5 days to complete one full loop. What excited people most was this: Proxima b sits in what's called the habitable zone, the sweet spot where temperatures could allow liquid water to exist. Not so close that water boils away. Not so far that it freezes solid. At the time, headlines exploded: a potentially life-bearing planet right next door. A second Earth just 4 light-years away. Scientists, though, were more cautious. They knew that being in the habitable zone does not automatically make a planet habitable. Mars once lay within the Sun's habitable zone too, and today it is nothing more than a cold, rocky desert. For a planet to truly support life, it needs more than the right distance. It needs an atmosphere to trap heat and create pressure so liquid water can exist. It needs a magnetic field to shield it from cosmic radiation. It needs the right chemical ingredients. For 7 years, Proxima b was just a number on paper. A dot on a chart. No one knew what it really looked like. Did it have an atmosphere? Oceans? Or was it just a dry, airless rock like the Moon? Until December 2023, when the James Webb Space Telescope turned its gaze in that direction. For the first time in history, humanity could truly look at the closest planet beyond our solar system. When the Webb data was processed, the first thing scientists noticed made them check their instruments again and again. Proxima b has an atmosphere. Not a faint hint of a few stray molecules. A real atmosphere. Dense. Structured. Earth-like. You might think, so what? Plenty of planets have atmospheres. True. But Proxima b is not an ordinary planet. It orbits a star scientists often describe as a monster. Proxima Centauri is a red dwarf. These stars are much smaller than our Sun, only about 1/8 its size. They are cooler and dimmer. But don't let their small appearance fool you. Red dwarfs are among the most violent stars in the universe. They erupt. Suddenly and without warning, their surfaces unleash massive bursts of energy called flares. These flares are almost unimaginable in power. In minutes, they can increase a star's brightness tenfold, even 100-fold. They blast out ultraviolet radiation, X-rays, and charged particles moving at near light speed. Our Sun has flares too. But the Sun's flares are a house cat compared to a tiger. Proxima Centauri's flares are thousands of times stronger, and they happen often, sometimes several times a week. Now imagine you are a planet orbiting a star like that. Every flare sends a tsunami of energy crashing into you. It slams into your atmosphere like a hyperhurricane, stripping gas molecules away and blowing them into space. In theory, a small planet like Proxima b should not survive this. Its gravity is too weak to hold on to an atmosphere under constant assault. Within a few 100 million years, the atmosphere should be completely gone, leaving behind a bare, scorched rock. That is what every computer model predicted. That is what scientists expected Webb to find. But reality was completely different. The atmosphere was still there. After 4 billion years of relentless stellar attacks, it was still there. This is impossible, one scientist said during an emergency meeting after the first night of observations. According to every calculation we have, this atmosphere should have vanished long ago. But it's still there, another replied. Which means, either our theories are wrong, the first concluded, or there's something we haven't accounted for. The second day of observations brought even more surprises. As scientists dug deeper into the spectral data, they realized Proxima b's atmosphere wasn't just a thin shell of gas clinging to the surface. It had structure. Multiple layers, much like Earth's atmosphere. On Earth, we have the troposphere at the bottom, where clouds form and weather happens. Above that is the stratosphere, then the mesosphere, then the thermosphere. Each layer has different temperatures, pressures, and chemical compositions. Proxima b showed similar layers. The data revealed temperature changes with altitude. Signs of moving air, winds flowing through the atmosphere. Look at this, Sarah said, pointing at a graph. These are cloud signatures. Clouds. Which means water vapor is condensing into tiny droplets suspended in the air. Just like on Earth. There's a water cycle, someone else said. Water evaporates from the surface, forms clouds, then falls back down as rain. A complete cycle. This was huge. A water cycle isn't just about water. It's about energy. When water evaporates, it carries heat from the surface upward. When it condenses into clouds, it releases that heat. This drives atmospheric motion, creating winds and weather. On Earth, the water cycle is one of the most important systems regulating climate. It moves heat from the equator toward the poles. It cools hot regions and warms cold ones. It creates a stable environment where life can thrive. Proxima b appeared to have something similar. This isn't a dead rock with a bit of gas, Sarah said slowly, staring at the screen. This is a living world. The word living made the room fall silent. No one dared to speak. They all knew that once that word was used, it would spread. The media would seize it. The public would erupt with excitement. Expectations would skyrocket. They had to be careful. They needed more evidence. They needed to be sure they weren't making a mistake. And yet, inside, every one of them felt the same electric thrill. Because what they were seeing looked like nothing they had ever seen before. That second night, an emergency video meeting was called. Leading scientists from around the world joined in, from the United States, Europe, Japan, Australia. Together, they examined the data. Together, they argued. The biggest question wasn't what was there. It was how it could possibly be there. Every model we run gives the same result, a professor from MIT said. With Proxima Centauri's flare activity, this planet's atmosphere should have been stripped away long ago. Could the planet be young? Someone suggested. Maybe it formed recently. Impossible, another countered. Proxima Centauri is an old star, around 5 billion years old. Its planets must be just as old. Then could the atmosphere be constantly replenished? Another voice asked. Volcanic activity, maybe? Possibly, Sarah said. But the amount of gas required would be enormous, far more than normal volcanism could provide. Unless, a professor from Cambridge began, then stopped. Unless what? Everyone pressed. Unless something is protecting the atmosphere, he said. Some kind of shield blocking the star's radiation. Like Earth's magnetic field. The room went quiet. The idea wasn't new. Earth's magnetic field, generated by the churning of molten iron in its core, acts as an invisible shield. It deflects charged particles from the sun, preventing our atmosphere from being blown away. But Proxima b is small. In theory, its core should have cooled long ago, no longer molten, no longer capable of generating a magnetic field. We need to check, Sarah said. Can Webb detect a magnetic field? Indirectly, an engineer replied. If there's a strong magnetic field, it will interact with Proxima's stellar wind and produce auroras. We should be able to see the light from those auroras. Then find them, Sarah said. That night, another team worked non-stop, filtering data, searching for auroral signatures. By morning, they found them. Not just auroras, but auroras spread across an entire hemisphere of the planet, powerful enough to stand out clearly in the data. A magnetic field, someone whispered. It has a magnetic field. Not a weak one. A strong one. Stronger than Earth's. That was the answer. That was why the atmosphere was still there after billions of years. Proxima b has a shield, a powerful magnetic field pushing back against the star's energy storms. But the next question was even harder. How could such a small planet sustain a magnetic field that strong? That question led them to the next discoveries that were even stranger than anything they had imagined. As the team analyzing the aurora data presented their findings, the room once again fell into silence. On the screen, a simulation of Proxima b appeared. Brilliant green ribbons of light, the unmistakable signature of auroras, were not confined to the two poles as they are on Earth. Instead, they stretched across the entire hemisphere facing the star. This is something we've never seen before, said Dr. Michael Chen from the University of California, his voice trembling with excitement. On Earth, auroras appear only near the magnetic poles. On Proxima b, half the planet is glowing. Auroras, or polar lights, occur when charged particles from the sun collide with a planet's atmosphere. On Earth, our magnetic field funnels these particles toward the poles, where they slam into atmospheric gases and paint the sky with shimmering curtains of light, the northern lights over Norway and Iceland, the southern lights over Antarctica. But for auroras to appear on such a vast scale as they do on Proxima b, the planet's magnetic field would have to be extraordinarily strong. Strong enough to create a massive protective bubble enveloping an entire half of the world. I reran the model 3 times, Chen continued, sliding his hand across the computer screen. To produce auroras at this level, Proxima B's magnetic field has to be 5 to 7 times stronger than Earth's. An elderly professor from Oxford looked up. 7 times? Are you certain? Yes, Professor, Chen nodded. Possibly even more. Our data isn't detailed enough for an exact figure, but 5 times is the absolute minimum. That single insight completely reshaped how they viewed Proxima B. A magnetic field acts like an invisible shield. You cannot see it or touch it, yet it is there, a vast, unseen web of magnetic forces stretching into space. When flares erupt from Proxima Centauri, they hurl billions of tons of charged particles toward the planet. These particles race through space at millions of kilometers per hour, carrying enough energy to strip away an atmosphere, destroy organic molecules, and turn a planetary surface into a radiation-blasted wasteland. But when they encounter Proxima B's magnetic field, they are pushed aside. Magnetic forces bend their paths, forcing them to slide around the planet instead of crashing straight into it. Like water from a shower hitting an umbrella, the stream cannot pass through and is diverted to the sides. That's why the atmosphere is still there, Sarah said during the afternoon meeting. The magnetic field has been protecting it for 4 billion years. Yet a new question emerged, one no one could answer. How could a small planet like Proxima B, only slightly larger than Earth, sustain such an incredibly powerful magnetic field? On Earth, the magnetic field is generated by a process known as the dynamo effect. Deep within the planet, nearly 3,000 kilometers below the surface, lies a molten iron core. As this core rotates, liquid metal flows and churns, acting like a colossal generator that produces the magnetic field. But this process requires energy. It requires heat. Earth can sustain it because we are large enough. Our core still retains heat from the planet's formation billions of years ago, supplemented by heat from radioactive decay deep underground. Smaller planets cool more quickly. Mars, only about half the size of Earth, lost its magnetic field billions of years ago. Its core cooled, solidified, and stopped moving. With no magnetic shield left, its atmosphere was gradually stripped away, leaving the dead, barren world we see today. Proxima B is roughly Earth-sized. In theory, its core should have cooled at least partially by now. Its magnetic field, if it still existed at all, should have been weaker than Earth's. And yet reality showed the opposite. Its magnetic field was far stronger. Could the planet have a different composition? A planetary geologist suggested. Maybe its core is richer in iron than Earth's. Even that wouldn't be enough, another scientist objected. A field this strong doesn't just need more iron. It needs intense motion in the core. It needs a continuous energy source to drive that motion. What about tidal forces? Another voice asked. It was an intriguing idea. Tidal forces, the gravitational pull from the star, can stretch and squeeze a planet as it orbits. This process generates internal friction, producing heat. It is like bending a metal wire back and forth until it grows warm in your hands. On Io, a moon of Jupiter, tidal forces are so extreme that they make it the most volcanically active body in the solar system. Its surface constantly erupts with lava, forever reshaping itself. Proxima B is extremely close to its star, Sarah said thoughtfully. The tidal forces there must be enormous. Maybe strong enough to keep the core molten, still in motion. That might be part of the answer. But it was not enough. Too much remained unexplained. What they did know for certain was this: Proxima B possesses a formidable defense system. A magnetic field powerful enough to fend off the energy storms from one of the most violent stars in the galaxy. But the story did not end there. Because as scientists continued to analyze the data, especially the composition of the atmosphere, they discovered something even more astonishing. Something that, if confirmed, would completely change how humanity sees its place in the universe. On the third day of observations, the chemical analysis team presented their report. Dr. Rachel Martinez, an atmospheric chemist from NASA, stood in front of the projection screen with a serious expression. "We analyzed the absorption spectra from Proxima B's atmosphere," she began. "The results show the presence of 3 major gases." A chart appeared on the screen, colorful lines crossing the graph, each one representing a different gas. First, water vapor. At a fairly high concentration, around 3 to 5% of the total atmosphere. This makes sense, we already know the planet sits within the zone where liquid water could exist. People nodded. Water vapor was not a surprise. Second, oxygen. Free oxygen, not bound to other elements. About 400 parts per million. The room grew quiet. Free oxygen was a big deal. On Earth, most atmospheric oxygen comes from plants, from photosynthesis. Other natural processes can produce oxygen, but they rarely generate it in such large amounts. Third, Martinez paused, scanning the room. Methane. Roughly 2 parts per million. Someone stood up. "Are you sure? Did you double-check the data?" "We checked it 5 times, Martinez replied. "The signal is very clear. There is methane in Proxima B's atmosphere." Now you might be wondering, so what? Why is everyone reacting like this? To understand that, you need a bit of chemistry. Oxygen is an extremely eager substance. It loves to react with things. When iron rusts, that's oxygen reacting with iron. When wood burns, that's oxygen reacting with the carbon in the wood. When you breathe, the oxygen in your lungs reacts with sugars in your blood to release energy. Methane is similar. It is also highly reactive. When oxygen meets methane, they react. Methane burns in oxygen, producing carbon dioxide and water. This reaction happens naturally, without needing high heat or pressure. On Earth, we have both oxygen and methane in our atmosphere. But they do not coexist naturally. They exist only because biological processes are constantly replenishing them. Plants produce oxygen through photosynthesis. Bacteria in swamps, in animal guts, and in the oceans produce methane. Without these biological processes, atmospheric oxygen would quickly react away with other substances. Methane would disappear just as fast. Martinez advanced to the next slide. Here's the problem. I calculated the lifetime of oxygen and methane in Proxima B's atmosphere. An equation appeared on the screen, dense with chemical symbols. With the temperature, pressure, and concentrations we observe, oxygen and methane would react with each other within. She paused, glanced back at the screen as if to be sure, about 100 years. 100 years, someone echoed. You mean? I mean that according to basic chemistry, oxygen and methane cannot coexist in an atmosphere for more than about a century, Martinez said plainly. They destroy each other. The room sank into a heavy silence. But they're still there, Sarah said softly. We're seeing them right now. Exactly, Martinez nodded. Which can only mean one thing. There must be some process continuously adding both oxygen and methane to the atmosphere, a process strong enough to replace what's lost to chemical reactions. An older professor from MIT spoke up. Could it be volcanoes? Geological activity can release both gases. Possibly, Martinez said. But I ran the numbers. To maintain these concentrations, volcanic activity would need to be thousands of times stronger than what we see on Earth today. The planet would need millions of volcanoes erupting constantly. Do the data show anything like that? Someone asked. Martinez shook her head. No. We see no signs of extreme volcanic activity. No excessive sulfur dioxide. No volcanic dust in the upper atmosphere. A biologist from the Pasteur Institute in France raised his hand. There is another possibility. All eyes turned toward him. On Earth, he said slowly, we have oxygen in the atmosphere because of plants. We have methane because of bacteria. Both of these processes, oxygen-producing photosynthesis and methane-producing fermentation, are biological. No one spoke. But everyone understood what he was implying. I'm not saying Proxima b has life, he continued. I'm only saying this is one possible explanation, one we shouldn't dismiss just because it sounds bold. Sarah stared at the chart on the screen. The lines representing oxygen, methane, and water vapor. They looked eerily similar to models of Earth's atmosphere billions of years ago, before plants evolved, when only bacteria existed. We need more data, she said at last. We need to look for other biosignatures. Phosphine, ammonia, gases that only biological processes produce in significant amounts. Can Webb detect those? Someone asked. Yes, Martinez replied. But we'll need longer observation time. 3 days isn't enough to catch signals from rarer gases. Then we'll request more time, Sarah decided. This could be the most important discovery in the history of science. We can't afford to miss this. But even as they planned the next round of observations, the data from those first 3 days still held mysteries they hadn't yet uncovered. What they would find next would split the scientific community into two camps, believers and skeptics. The debate would last for months. Because it was no longer just scientific data. It was a signal. A signal repeating with almost unbelievable precision. Three days after the meeting on atmospheric composition, a press release was drafted. Then scrapped. Then rewritten. Then scrapped again. The problem was not a lack of information. It was too much information that, if released carelessly, could trigger waves of panic around the world. Sarah sat alone in her small office, staring out the window at the night sky. Somewhere out there, 4.37 light-years away, a planet was challenging everything she thought she knew. Her phone rang. The institute director. We need to make a decision, he said. The press has caught the scent. CNN called asking about a breakthrough discovery at Alpha Centauri. They are going to run the story whether we comment or not. Sarah exhaled slowly. I know. But if we get this wrong, if we create false hope. Then what? He asked. We're scientists. Our job is to report what we find, not to hide it because we're afraid of how the public might react. But that word, Sarah said quietly. That word, life. Once we say it. There's no taking it back, he finished. I get it. But Sarah, look at the data. What do we actually have? She opened her laptop and pulled up the summary table. Oxygen. Methane. Water vapor. All coexisting in a stable atmosphere. An unusually strong magnetic field. An active water cycle. A multilayered atmospheric structure. Every sign, she admitted, points in the same direction. Then we tell the truth, he said. We say it's a hypothesis. We say we need more evidence. But we don't pretend the possibility isn't there. The next day, the press conference was held. Not in a massive auditorium packed with reporters like in the movies, but in a small conference room, with only a handful of science journalists invited. Sarah stood at the microphone, the printed statement trembling slightly in her hands. Based on data from the James Webb Space Telescope, she began, we have identified that Proxima Centauri b, the closest known exoplanet to Earth, possesses an active atmosphere with an unusual chemical composition. She paused, looking at the attentive faces in front of her. This atmosphere contains free oxygen alongside methane in significant concentrations. According to chemical models, these two gases cannot coexist for long periods unless there is a continuous process replenishing them. A reporter raised a hand. What kind of process? Sarah took a deep breath. We don't know for certain. There are 3 main possibilities. She advanced to the next slide. First, extremely intense geological activity, volcanoes or hydrothermal systems, releasing these gases. However, we have not observed evidence of activity at the required scale. Second, an unknown chemical process, possibly driven by stellar radiation or reactions deep within the planet. This is something we are actively investigating. She stopped. The room was silent. Third, a biological process. Similar to Earth, where plants produce oxygen through photosynthesis and microbes produce methane through fermentation. A murmur rippled through the room. Cameras flashed. I want to emphasize, Sarah said more firmly, that this is only one of 3 hypotheses. We are not claiming that life exists on Proxima b. We are saying that it is a possibility that deserves serious investigation. But if it is life, one reporter asked, would this be the first time we found evidence of life beyond Earth? If confirmed, Sarah stressed the word if, then yes. But we are still very far from that point. We need much more data. What kind of data? Someone else asked. Martinez, seated beside her, spoke up. We need to search for additional biosignature gases. Phosphine, for example, a gas that on Earth is produced only by bacteria. Or dimethyl sulfide, which is generated by marine algae. These would be far clearer biological fingerprints. How long until we know? Came the next question. Webb needs at least 20 more hours of observation time, Sarah replied. We've submitted a request. If it's approved, within 6 months we may have clearer answers. The press conference ended after an hour. But what was said there spread like wildfire. The next day's headlines screamed. Possible signs of life found on nearest exoplanet. NASA, Proxima b may be capable of supporting life. Do we have neighbors in space? Sarah winced as she read them. They had been careful. They had emphasized uncertainty. But the media, as always, focused on the most dramatic angle. The scientific community was split. One camp was supportive. This is how science should work, a Harvard astronomy professor wrote on Twitter. We have data. We form hypotheses. We test them. Don't be afraid of big questions. The other camp was skeptical. They're rushing, a planetary scientist from the University of Arizona argued. There isn't enough data to make claims about biology. This is bad science. The debate dragged on for weeks. Scientific forums buzzed with arguments. Paper responded to paper. Model clashed with model. But while scientists argued publicly, another group, those working directly with Webb's raw data, found something else. Something they weren't sure should be made public at all. Because it didn't fit any natural model they knew. Dr. David Park, a signal processing specialist, had spent 3 weeks filtering noise from Webb's infrared data. Tedious, repetitive work. Most of it was random interference from instruments, cosmic radiation, and hundreds of other sources. But one signal kept coming back. Not strong, but clear. And repeating. At first, he assumed it was an instrumental error. He checked everything, the detectors, the filters, the processing software. Nothing was wrong. He reprocessed data from other Webb observations. No similar signal appeared. It only showed up when Webb was observing Proxima b. He zoomed in and analyzed it closely. Small pulses in the infrared, signatures of heat. They appeared at regular intervals, every 11.2 hours. 11.2 hours. Exactly the time Proxima b takes to complete one rotation around its star. He called Sarah at 2 in the morning. You need to see this, he said. Now. An hour later, Sarah stood in his lab. Her eyes were red from lack of sleep, but the moment she saw the graph on the screen, the fatigue vanished. This is from Proxima b? She asked. Yes, Park nodded. A thermal signal, repeating exactly with the planet's rotation period. Sarah studied it. Each pulse lasted about 15 minutes. Nearly identical intensity. The spacing between pulses, 11.2 hours. Error margin less than 1,000th. Is there any natural phenomenon that produces something this regular? She asked. Park shook his head. I've looked everywhere. Volcanoes erupt randomly. Hydrothermal vents aren't strong enough for Webb to detect from that distance. Seismic activity doesn't follow a fixed cycle. Could it be reflected starlight? Sarah suggested. As the planet rotates, maybe a region reflects more light. I thought of that, Park said. But this is thermal emission, not reflected light. Something on the planet is releasing heat. For a fixed duration. Then stopping. Then turning back on exactly 11.2 hours later. They stood in silence, staring at the graph. Do you think, Sarah began, then stopped. Think what? Park asked. No, she shook her head. I won't say it. It's too crazy. For 3 weeks, Park said quietly, I've tried not to think it. But Sarah, I can't find any natural explanation. No geological process is that precise. Nature always has randomness. Sarah looked out the window. The sky was beginning to brighten, dawn approaching. We need more eyes on this, she decided. We don't release it. Not yet. But we call a small group of experts, physicists, geologists, biologists. See if anyone can come up with an explanation. The closed meeting was convened a week later. Just 10 people. Everyone signed strict non-disclosure agreements. They spent 3 days analyzing the data. 3 days of arguments, calculations, and modeling. In the end, they had no conclusion. Only more questions. If this goes public, someone said, the scientific community will explode. Half will say we've lost our minds. The other half will demand Webb observe it 24 hours a day. So what do we do? Sarah asked. We wait, said an elderly professor from Caltech. We request more observation time. We look for clearer biosignatures, phosphine, ammonia, other gases. If we find those, then we talk about this signal. And if we don't, someone asked. Then maybe it's just a strange geological phenomenon we don't yet understand, he replied. The universe is full of strange things. Not every mystery is aliens. They agreed. The thermal signal would remain confidential. The focus would stay on searching for unmistakable biological evidence. But information has a way of leaking. 3 months later, a paper appeared anonymously on a scientific forum. A mysterious repeating signal from Proxima b, natural or artificial. The story exploded. This time, not just within science. The entire world was watching. What began as a simple scientific observation was turning into one of the biggest questions humanity has ever faced. Are we alone in the universe? The answer might be right there, just 4.37 light-years away. Close enough that within the lifetimes of children born today, we might send a probe there. But first, they needed to understand more. More data. More discoveries. And the discoveries coming next would make this story far more complicated than anyone expected. March 2024. 6 months after the first observation, Webb was granted another 30 hours to observe Proxima b. This time, not to search for biosignatures, but to better understand a strange thermal signal. Dr. Park assembled a separate team, 5 people, all specialists in signal processing. They worked in a small, isolated room. No one was allowed in without special clearance. The new data arrived. More of it. Richer. Clearer. The signal was still there. Still repeating with perfect regularity. 11.2 hours. A margin of error below 1/10,000th. But this time, with higher resolution data, they saw something else. Something that made everything far stranger. The signal did not come from a fixed point on the planet's surface. It moved. Each time it appeared, it was in a slightly different location. But always within the same region, an area about 500 kilometers wide, right along the boundary between the day side and the night side. It's like something is moving along the twilight line, Park said during a closed meeting. Always where the temperature is moderate. Always where the star's light hits at an angle. Could any atmospheric phenomenon explain this? Sarah asked. A planetary climate expert shook his head. Winds? Maybe. But winds don't have cycles that precise. They vary with seasons, temperature, countless factors. Not down to the second. Hot ocean currents, someone else suggested. Like the Gulf Stream on Earth? Unlikely, Park replied. Ocean circulation can be cyclical, but never this exact. Nature doesn't work like a clock. The room fell silent. Nature doesn't work like a clock. And yet this did. Park advanced to a new slide. I compared this signal to every known natural periodic phenomenon. The screen filled with graphs. Volcanoes. Hydrothermal vents. Tides. Ocean waves. Seismic activity. Winds. Ocean currents. Every natural process shares one thing, he explained. Variability. Random noise. Sometimes stronger, sometimes weaker. Slight shifts in period. Because nature is influenced by thousands of interacting factors. He switched to the next slide, the signal from Proxima b. But this? No variation. No noise. Every pulse identical to the one before it. The period never changes. The intensity stays constant. What does that mean? Someone asked, even though they already knew. There are two possibilities, Park said slowly. One, there is a natural process we don't yet know, something entirely new, never before observed, that produces extraordinary precision. He paused. Two, this is not a natural process. No one spoke. But everyone understood what he was implying. Sarah stood up. We can't jump to that conclusion. We don't have enough data. There's too much we still don't understand about Proxima b. I know, Park nodded. I'm not saying this is proof of anything. I'm presenting the data. Other experts may find explanations we've missed. But over the next 3 months, no matter how many specialists they invited, geologists, meteorologists, physicists, no one could offer a fully convincing explanation. A professor from Princeton suggested seismic resonance, waves trapped within the planet's crust producing steady oscillations. But calculations showed that achieving such precision would require an internal structure so uniform it bordered on impossible. A physicist from Tokyo proposed plasma phenomena, magnetic loops creating hot plasma regions orbiting the planet. But that failed to explain why the signal remained confined to the day-night boundary. A fluid dynamics expert from Cambridge suggested standing waves in a global ocean, like water sloshing in a bathtub. But sustaining waves with such exact timing for years would require a continuous external energy source. Every hypothesis had flaws. Every model fell short. In June 2024, an international exoplanet conference was held in Geneva, Switzerland. More than 300 scientists from 50 countries attended. Most of the conference was routine, presentations on new discoveries, observational techniques, theoretical models. But on the afternoon of the third day, when Park presented the Proxima b signal, the atmosphere in the room changed completely. After his talk, the Q&A session lasted nearly 2 hours. Not polite questions, but heated debate. What are you implying? A professor from Germany asked bluntly. Are you saying this is an artificial signal? I'm not implying anything, Park replied calmly. I'm presenting the data. And the fact that we have not found a satisfactory natural explanation. Because you haven't looked hard enough, someone shouted. The universe is vast. There are billions of phenomena we don't understand. You can't jump to aliens because of one strange signal. I agree, Park said. That's exactly why we publish the data, so the global scientific community can analyze it. Someone here may have an idea we haven't considered. A young scientist from Brazil spoke up. What are the odds of intelligent life on a planet just 4 light-years away? Extremely low. We're letting imagination override science. And what are the odds of a natural process producing a signal precise to a 10,000th of a second for years? Another voice countered. Also extremely low. Sarah, seated in the front row, stood. Everyone, we're losing focus. The question isn't aliens or not. The question is what we understand, and what we don't, about Proxima b. We need more data, not more arguments. But the arguments didn't stop. They spilled out of the auditorium, into hallways, into cafes. Scientists split into 2 clear camps. One camp, the strict naturalists, insisted that every phenomenon must have a natural explanation. Not finding it yet doesn't mean it doesn't exist. It means more research is needed. Jumping to intelligent life without direct evidence is unscientific. The other camp, the open camp, did not claim the signal was extraterrestrial, but refused to rule it out. Science must follow data, not belief. If data doesn't fit existing natural models, other possibilities must remain on the table. The media seized the story almost immediately. Headlines spread across the world. A mysterious signal from Proxima b divides scientists. Aliens or nature? Scientists can't agree. Is this a greeting from the cosmos? Sarah sat alone in her Geneva hotel room, reading the headlines with a sinking feeling. This was exactly what she had feared. The story was spiraling out of control. Science was turning into spectacle. Her phone rang. An unfamiliar number. Sorry to bother you, a man's voice said. This is Professor Robert Chen from the SETI Institute. I think we need to talk. SETI, the Search for Extraterrestrial Intelligence, an organization that had spent decades listening for radio signals from space, hoping to catch a message from another civilization. About what? Sarah asked, already knowing. About your signal, Chen said. We have some data you might want to see. From our radio telescopes. Sarah straightened. You've been observing Proxima b? We've been observing it for 20 years, Chen replied. Since its discovery in 2016. It's one of our primary targets. The nearest planet in the habitable zone. What did you find? Sarah asked, her voice trembling slightly. Chen hesitated. That's why I'd prefer to meet in person. Some of our data is complicated. Can you come to California? A week later, Sarah sat in a dim conference room in Mountain View, California. On the large screen, graphs displayed 20 years of radio data from the direction of Alpha Centauri. We scan many frequencies, Chen explained. But we focus on a few in particular. One of them is 1420 MHz. Sarah knew that frequency. The hydrogen line, the most abundant element in the universe. In SETI circles, it's often called the water hole, because hydrogen plus oxygen makes water. If someone wanted to get another civilization's attention, this would be the frequency to use. What did you find? She asked. Chen zoomed in on a section of the graph. Most of the time, there's nothing but background noise. But occasionally, he pointed to a thin spike, we detect a narrowband signal. Very narrow. Just a few hertz wide. In space, most natural radio sources emit across a broad range of frequencies, like white light containing every color. A narrowband signal, concentrated at a single frequency, usually comes from a deliberate transmitter. Like a radio station on Earth. When does this signal appear? Sarah asked. Not often, Chen said. We first detected it in 2018. Then it disappeared. It came back in 2020, then vanished again. In 2023, it appeared 3 times. This year, twice. Any pattern? Chen shook his head. Nothing obvious. But there's one strange thing. Each time it appears, it lasts about 15 minutes. 15 minutes. Exactly the duration of each thermal pulse Park had detected. Sarah's heart began to race. Did you check whether the radio signal lines up in time with the thermal pulses? We did, Chen nodded. Our timing resolution isn't perfect, but it appears there may be a correlation. The room fell silent, broken only by the low hum of computers. The source of the radio signal? Sarah asked. We're not sure, Chen admitted. It could be Proxima b. It could be the star. It could be something else in the system. Our resolution isn't high enough to pinpoint it. What do you think this is? Chen met her gaze. Do you want my personal opinion, or the Institute's official stance? Personal. He exhaled slowly. After 20 years in this field, after thousands of hours listening to the universe, I've learned one thing. Never rush to conclusions. 99% of the signals we get excited about turn out to be satellites, aircraft, or instrument errors. He paused. But the remaining 1%? We don't know. They disappear before we can confirm them. Like this one. So what do you think about Proxima b? Chen looked back at the screen. I think we need far more data. Much more. We need bigger, more sensitive radio telescopes. Continuous observation, not a few hours at a time. We need global coordination. How much would that cost? Hundreds of millions of dollars, Chen said. Possibly $1 billion, depending on scale. Would anyone fund that? Chen smiled wearily. After you published the atmospheric data, donors started calling. They want to know if we have plans for Proxima b. If we present it the right way, I think the money could be there. Sarah looked out the window. Outside, the sun was setting, the sky shifting from blue to orange, then purple. Somewhere out there, 4.37 light-years away, a planet was sending signals no one understood. Maybe it was just nature. Maybe it was something else. The answer was waiting. But to find it, humanity would have to decide whether it dared to ask the question at all. While the world's attention was locked onto Proxima b and its unanswered mysteries, a small group of scientists quietly focused on a different target in the same star system. Proxima Centauri c. This planet was discovered in 2019, 3 years after Proxima b. It is larger, farther out, and far colder. About 7 times the mass of Earth. Roughly 1.5 astronomical units from its star, farther than the distance between Earth and the Sun. At that distance, temperatures on Proxima c are brutally low. -230 degrees Celsius, possibly even colder. This is not the kind of place where you would expect anything interesting. Just a frozen mix of ice and rock, circling in the dark. At least, that is what everyone thought. Dr. Lisa Wang, a young planetary scientist from the University of Tokyo, spent 6 months carefully analyzing Webb telescope data focused on Proxima c. The work was tedious. Most of her colleagues were obsessed with Proxima b, where all the exciting discoveries seemed to be happening. No one cared about a distant, frozen world. But Wang had a hypothesis. She suspected that Proxima c might not be a native member of the system at all. It might have come from somewhere else. Its orbit is a bit strange, she explained during a small group meeting in July. It does not lie in the same plane as Proxima b. The tilt is about 30 degrees. In our own solar system, the planets orbit the Sun in nearly the same plane, like stacked vinyl records. That makes sense, because they all formed from the same rotating disk of gas and dust around the young Sun. But when a planet's orbit is strongly tilted compared to the others, it can point to a turbulent past. Maybe it formed elsewhere and was later pulled in. Maybe it suffered a massive collision that knocked it off course. Did Webb see anything on its surface? Someone asked. Wong nodded and pulled up an image on the screen. This is where it gets interesting. We cannot see the surface directly, it is too far away and too dark. But the spectral analysis shows. She paused and checked the numbers again. Shows what? Someone pressed. It shows that it has an atmosphere. The room went quiet. Then someone laughed. An atmosphere on a planet at minus 200 degrees. Everything should be frozen solid at that temperature. Normally, yes, Wong agreed. But the data are very clear. There is a thin envelope of gas around the planet, mostly hydrogen with some helium. Similar to the atmospheres of gas giants. So Proxima c is a gas planet? Someone asked. Not exactly, Wong said, shaking her head. Its mass suggests a very large solid core, probably rock mixed with ice. The gas layer is only a small fraction of the total mass. A mini Neptune, someone said. A solid core wrapped in a thick atmosphere. Wong nodded. Exactly. These kinds of planets are fairly common in the universe, but they are usually found much closer to their stars. Finding one this far out is unusual. Unusual, another voice finished. But the most intriguing discovery about Proxima c was not its atmosphere. It was something Wong found while analyzing high-resolution infrared images. Around Proxima c, there was a ring. Not a dramatic ring of rocks like Saturn's, but a thin ring of dust and ice. Fainter and less spectacular, but unmistakable in the data. This ring is about 50,000 kilometers wide, Wong explained during an online conference in August. It is very thin, probably only a few hundred meters thick. It consists mostly of fine dust particles mixed with water ice. On the screen, a simulation of Proxima c appeared, a dim bluish sphere with a pale white ring encircling it. How does it even have a ring? Someone asked. There are two main possibilities, Wong said. First, it could be leftover material from the planet's formation. When Proxima c formed, some material may not have fully accreted and remained as a ring. But you do not believe that, someone remarked. Wong smiled. Not really. If this were leftover formation debris, the ring would be extremely old, about 4 billion years. Over that time, the dust would slowly spiral down into the planet due to drag from the thin atmosphere, or be blown away by stellar wind. The ring should not have survived this long. So what is the second option? The second option is that the ring is young, Wong said. Created by a relatively recent event, in cosmic terms. A collision, perhaps. A collision, when a large asteroid or a small moon slams into a planet at tremendous speed. The impact ejects billions of fragments into space. Some fall back to the planet. Some escape entirely. But some become trapped in orbit, forming a ring. When did it happen? Someone asked. It is hard to say exactly, Wong replied. But based on the density and distribution of the dust, I estimate within the last 1 million years. Possibly even more recent. A million years sounds like a long time. But for a planet that is 4 billion years old, it is basically yesterday. That suggests the Alpha Centauri system is still active, a planetary geologist said. Still experiencing impacts, still changing. Not an old, quiet system like we assumed. Wong nodded. Exactly. That is one of the reasons I think the history of this system is far more complex than we imagined. She switched to the next slide, a computer simulation. I ran several models of the dynamical history of the Alpha Centauri system. 3 major stars, at least 2 known planets, and possibly several others we have not detected yet. All interacting through gravity. On the screen, orbits appeared as tangled, looping curves, weaving through one another. The results suggest the system is not stable over long timescales. In the first few billion years, there may have been many more planets. Over time, they collided with each other or were flung out into interstellar space. So Proxima c could be one of the survivors, someone asked. Possibly, Wang said. Or it could be a wanderer, a rogue planet drifting through space, that was later captured by Proxima Centauri. The idea of rogue planets is no longer exotic. Scientists estimate there may be billions of them in our galaxy alone, worlds ejected from their parent systems, drifting through eternal darkness. Occasionally, a passing star can capture one and pull it into orbit. If Proxima c is a captured rogue planet, someone mused, then it could be carrying secrets from an entirely different star system. Maybe from very far away. Wang smiled. Exactly. Studying its composition could tell us where it came from. But doing that would require more observation time. More detailed data. And Webb did not have much time to spare for Proxima c, because everyone wanted to look at Proxima b. Even so, the discoveries surrounding Proxima c mattered. They painted a picture of a star system with a violent, chaotic history. A place where collisions still happen. Where planets can migrate from one orbit to another. That picture would become even more important when scientists began uncovering strange findings around the system's main stars, Alpha Centauri A and B. Findings with no easy explanations at all. To understand what is really happening in the Alpha Centauri system, we need to take a step back and look at the bigger picture. Alpha Centauri is not a single star. It is a system of 3 different stars, born at the same time but separated very early in their lives. Alpha Centauri A is the primary star, the largest of the 3. It has about 1.1 times the mass of the Sun. It is slightly brighter, slightly hotter, with a pale yellow color, much like our own Sun. Alpha Centauri B is a bit smaller, about 90% the mass of the Sun. It is slightly dimmer, slightly cooler, glowing with a soft orange hue. These 2 stars orbit each other in an eternal dance. The distance between them changes along an elliptical path, sometimes comparable to the distance between the Sun and Saturn, sometimes much farther. It takes about 80 years for them to complete a single orbit. Then there is Proxima Centauri, a tiny red dwarf. It sits about 13,000 astronomical units away from the A-B pair, nearly 200 times the distance between Earth and the Sun. At that range, the gravitational pull between Proxima and the other 2 stars is extremely weak. It takes Proxima millions of years to complete one slow orbit around the system's shared center of mass. Professor Michael Foster of the University of Cambridge has spent 30 years studying the dynamics of multiple star systems. He is considered one of the world's leading experts in the field. Triple star systems are very difficult to keep stable, he explained in an online lecture last September. Gravity pulling from 3 different directions creates chaos. In most cases, one star gets flung out, or 2 stars eventually collide. On the screen behind him, computer simulations played out different fates for triple star systems. Some survived for billions of years. Others fell apart after only a few million. Alpha Centauri is a special case, Foster continued. It has survived for about 5 billion years, roughly the same age as our Sun. That tells us its overall configuration must be fairly stable. But, he emphasized, stable does not mean calm. Foster brought up a new simulation. We ran models of planet formation in the Alpha Centauri system, and the results were fascinating. On the screen, 3 stars appeared, each surrounded by vast disks of gas and dust. Inside those disks, tiny grains collided, stuck together, and slowly grew into larger and larger bodies. Each star has its own planet-forming region, Foster explained. Around Alpha Centauri A, multiple planets could form. The same is true for B. Proxima has its own region as well. In the simulation, dozens of small planets emerged, orbiting their parent stars and gradually growing. But here's the problem, Foster said. The stars don't stay still. They tug on each other. Their orbits shift, and that affects the planets. Chaos began to unfold on the screen. A planet orbiting Alpha Centauri A was pulled too close to Alpha Centauri B. B's gravity warped its path. The planet spiraled inward and was swallowed by the star. Another planet was hurled outward, ejected into interstellar space at tremendous speed. It would wander forever, never to return. Two planets collided. The impact exploded into thousands of fragments. Some fell into a star. Some formed a dusty ring. Others kept orbiting, slowly clumping together to form a new planet. During the first few billion years, Foster said, Alpha Centauri may have had dozens of planets. But most of them didn't last. Destroyed by collisions. Consumed by stars. Or flung into deep space. By the end of the simulation, only a handful of planets remained. They occupied stable orbits, far enough away to avoid being eaten by their stars, yet close enough to avoid being thrown out. Proxima b is one of those survivors, Foster concluded. It endured 4 billion years of chaos. Collisions. Radiation. Gravitational tug-of-war between 3 stars. The fact that it is still there, and may still have an atmosphere, is remarkable. A student raised a hand. Professor, what does that mean for the possibility of life? Foster paused. That's a great question. Traditionally, we've assumed life needs stability, billions of years of calm conditions to evolve. But we may be wrong. He gestured toward the screen. It's possible that survival pressure, impacts, extreme climate shifts, constant challenges, actually push life to evolve faster, to become more resilient. On Earth, he continued, the most disruptive events, like the asteroid impact that wiped out the dinosaurs, actually opened the door for life to evolve in new directions. Without that event, we probably wouldn't be here. So, he concluded, a chaotic system like Alpha Centauri isn't necessarily hostile to life. It may be a forge, a place where only the toughest forms can survive. If life exists there, it likely won't resemble anything we know. The lecture ended, but the ideas lingered within the scientific community. A new way of thinking about life, not as something fragile that must be protected, but as something resilient, adaptive, capable of surviving extreme trials. This perspective may become crucial as scientists continue to uncover the mysteries of Proxima b, especially its unusual and intriguing state. While scientists argued over mysterious signals, atmospheric composition, and the chaotic history of the star system, another research group focused on a more basic but crucial aspect of Proxima b, how it spins. Dr. Amanda Rivera of the Arizona Planetary Institute spent 2 years analyzing Proxima b's rotation. It was not glamorous work. No sudden breakthroughs. Just meticulous measurements and patient calculations. Yet what she uncovered painted a dramatic picture of this world. Proxima b is tidally locked, she announced at a conference in October. Just like our moon. The moon always shows the same face to Earth. You never see its far side, not because it does not rotate, but because it rotates at exactly the same rate that it orbits Earth. One spin for every orbit. That is exactly what happens on Proxima b. It orbits Proxima Centauri in 11.2 hours. Its rotation period? Also 11.2 hours. That means one side of Proxima b always faces the star, locked in eternal daylight. The other side always faces away, trapped in endless night. On the day side, Rivera explained, the star hangs motionless in the sky. It never sets. Temperatures are extreme. The light is intense. Everything is constantly scorched. She switched to the next slide, a simulated image of the night side. The night side is the opposite. It never sees the star. It is plunged into permanent darkness. Temperatures drop to extremes. Everything freezes solid. It sounded like a terrible place to live. Too hot on one side. Too cold on the other. Nowhere in between. For many years, Rivera continued, this is why scientists believed tidally locked planets could not support life. The conditions seemed far too extreme. But, she said with a smile, we were missing one critical factor, the atmosphere. Rivera brought up a computer simulation. On the screen, Proxima b appeared sharply divided, one side blazing bright, the other pitch black. When we ran detailed climate simulations for Proxima b, we found something interesting. The atmosphere does not stay still. It moves. In the simulation, red arrows appeared, streams of hot air flowing from the day side to the night side. Blue arrows moved the opposite way, cold air returning from night to day. Air on the day side is heated, Rivera explained. It expands, pressure builds, and it is forced toward the night side. When it reaches the night side, it cools, contracts, and creates a low-pressure region that pulls more air from the day side. The result is a continuous circulation. Hot air flows from day to night. Cold air flows from night to day. A massive loop wrapping around the entire planet. Someone in the audience raised a hand. Does that mean temperatures even out? Exactly, Rivera nodded. The atmosphere acts like a giant heat pump. It carries heat from the day side to the night side, cooling the day and warming the night. But the most efficient region, she said, pointing to a band on the simulation, the boundary between light and darkness, is right here. The twilight zone. The twilight zone, a narrow band running along the boundary between day and night. A place where the star always sits on the horizon. Light arrives at a shallow angle, never directly overhead. Temperatures are neither too hot nor too cold. According to our models, Rivera said, temperatures in the twilight zone range from -20 to 20 degrees Celsius, depending on altitude and latitude. -20 to 20. A range where liquid water can exist. A range where life, at least life as we know it, could potentially survive. How wide is this region? Someone asked. About 1,000 kilometers, Rivera replied. Stretching all the way around the planet. Total area, she estimated quickly, around 50 million square kilometers. 50 million square kilometers. Nearly the size of Asia. A vast region with conditions that could be suitable for life. But that's just theory, a skeptical voice called out. How do we know the atmosphere actually behaves like that? Rivera smiled. That's a fair question. The reason I'm confident is because we tested it, using data from Webb. She pulled up a new chart. This is a temperature map of Proxima b created by the James Webb Space Telescope. Red shows the hottest regions. Blue shows the coldest. On the screen appeared a globe. One side glowing red. The other deep blue. But between them ran a band of yellow, orange, and green, intermediate temperatures. The twilight zone, Rivera said, pointing. It's real. Not just theory. We're seeing it. The room buzzed with excitement. This was the first time anyone had directly shown that a tidally locked planet could host a temperate region, not just on paper, but in reality. If there is liquid water on Proxima b, someone asked, where would it be? Rivera nodded. That's exactly what we're trying to figure out. On the day side, water would boil away. On the night side, it would freeze into ice. But in the twilight zone, she paused, letting the idea settle, water could remain liquid. There could be lakes, rivers, even small oceans. We can't confirm that yet, she added quickly. Webb doesn't have the resolution to see small surface bodies of water. But the spectral data shows water vapor in the atmosphere. That water has to come from somewhere. A biologist stood up. If there's liquid water in the twilight zone, combined with a stable atmosphere and moderate temperatures, this could be one of the most promising environments for life. Rivera nodded slowly. Perhaps. But life there would be very different from life on Earth. It would exist in a narrow band, forever locked in twilight. It would never experience sunrise or sunset like we do, because the star never moves in the sky. There would be no day and night. But maybe, she added, that's the advantage. A stable environment. No seasons. No changing day-night cycles. Just one region with constant conditions, ideal for life to adapt. That image, a narrow ring circling an alien planet, forever bathed in twilight, dotted with small oceans, with gentle winds blowing from day to night, began to take hold in everyone's imagination. If life exists there, it lives in a world utterly unlike Earth. A world where the sun never rises and never sets. A world of eternal dusk. But does such life really exist? The answer will come from future discoveries, findings that some already call near certain evidence, while others remain deeply skeptical. While most attention was focused on Proxima b, a small group of astronomers were intrigued by something entirely different: dust. Not dust on a planet, but dust in space, orbiting Alpha Centauri A, the system's primary and largest star. Dr. James Young from the University of Hawaii stumbled upon it while analyzing infrared data from the Webb Space Telescope. At first, he thought it was a data glitch, a faint glow around the star, like a halo. But after a closer look, he realized it wasn't an error at all. It was real dust. A lot of dust. Alpha Centauri A is about 5 billion years old, Young explained during an online conference in November. Roughly the same age as our Sun. At this stage, a normal star should be clean. Any dust left over from planet formation should have either been blown away or locked into planets. He pointed to a chart on the screen. But Alpha Centauri A has a dust disk. It's not massive, only about 1/10 the mass of disks around young stars. But it's still there. And it shouldn't be. How far out is this disk? Someone asked. About 1 to 3 astronomical units, Young replied. Roughly from Earth's orbit to halfway between Earth and Mars. A region that theory says should be cleared out after a few billion years. What's the temperature of the dust? Young checked his numbers. Around 300 Kelvin. About 27 degrees Celsius. Pretty warm. That was the second anomaly. Dust around an old star shouldn't be that warm. It should have cooled long ago. This means the dust is being heated, Young explained. Possibly by collisions. Possibly by friction as dust particles smash into each other. But to maintain this temperature, he continued, there has to be a continuous source of dust. Otherwise it would cool down quickly, spiral into the star, or get blown away. Young proposed 3 hypotheses to explain the dust disk. Hypothesis 1, a recent planetary collision. 2 planets, or a planet and a large asteroid, collided within the last few million years. The impact produced billions of tons of dust. That's the dust we're seeing. He switched to the next slide. Hypothesis 2, capture of an interstellar object. An asteroid or comet from interstellar space passed through the Alpha Centauri system and was captured by Alpha Centauri A's gravity. As it orbited the star, heat vaporized surface ice, producing dust. Hypothesis 3, he paused, is that there's a process we don't yet understand. Somehow, dust is being generated continuously from within the system. Which hypothesis do you believe? Someone asked. Young shook his head. There isn't enough data to be certain. But personally, I lean toward hypothesis 1, a recent collision. Because. He brought up a new slide. Because we found this. On the screen appeared a magnified image of the dust disk. Within it were 3 points brighter than the rest. 3 objects, Young said, pointing. Larger than typical dust grains. They could be fragments from a collision. Or they might be small asteroids. We need longer observations to determine exactly what they are. But their presence suggests that something dynamic happened in this system not too long ago. That revelation sparked a wave of new questions. If a planetary collision really did occur around Alpha Centauri A, what does that mean? Is the system still in a formative stage, or was this a rare, unusual event? More importantly, could that collision have affected Proxima b? Could debris from the impact have traveled toward Proxima, adding even more disturbance to that planet? For now, there are no answers. But these questions add depth to the picture of a star system that is active and not fully settled, a place where dramatic events may still be unfolding. And the next discovery tied to this dust disk would be stranger still. A finding that, even today, has no satisfying explanation. A discovery involving 3 fragments moving in ways nature shouldn't be able to produce. Two months after discovering the dust disk around Alpha Centauri A, Yang and his team were granted another 30 hours of observation time with Webb. This time, they focused entirely on 3 strange objects embedded in the disk. The work was tedious. Each observing session was spaced weeks apart. They photographed the positions of the 3 objects. Compared them. Calculated their orbits. Built models. After 6 months, they finally had enough data to determine the precise orbits of all 3. When the results appeared on his computer screen, Yang sat silently in his dark office, staring at the numbers, unable to believe what he was seeing. He reran the program. Same result. He called his research assistant. Check my code. See if there's any mistake. 2 days later, the assistant reported back. The code is working correctly, Professor. No errors. Yang called a colleague at Princeton and sent over the raw data. Can you calculate the orbits of these 3 objects for me? A week later, the results came back from Princeton. Identical. At that point, Yang had no choice but to accept the truth. The data were not wrong. The calculations were not wrong. What he was looking at was real. 3 objects were orbiting Alpha Centauri A. Their orbits were almost perfectly circular. At the same distance from the star, about 1.5 astronomical units. Moving at the same speed. But they were rotating in the opposite direction. Opposite to the dust disk. Opposite to the star's rotation. Opposite to everything else in the system. In January 2020, Yang published the discovery in a paper submitted to Nature. The title read, 3 retrograde orbiting objects around Alpha Centauri A challenge to planet formation theory. The reaction from the scientific community was swift. Not excitement, but deep skepticism. Your data must be wrong, wrote a professor from MIT in a referee report. There is no natural mechanism that can produce 3 objects with identical orbits rotating opposite to everything else. It could be a projection effect, another suggested. From our viewpoint, they may appear retrograde, but in reality they are not. Yang responded to every critique, one by one. He explained how he had ruled out projection effects. How he had used data from multiple observing campaigns. How he had worked with independent teams to confirm the results. I understand that this is hard to believe, he wrote. But the data are unambiguous. These 3 objects are orbiting in the opposite direction. That is an observational fact. The question is not whether, but why. Over the next 6 months, dozens of papers were published attempting to explain the phenomenon. A team from the University of Tokyo proposed that the objects might be remnants of a large planet that had been destroyed. When the planet exploded, perhaps due to a massive collision, some fragments could have been ejected in the opposite direction and later settled into retrograde orbits. But computer simulations showed this was extraordinarily unlikely. For 3 fragments of similar size, on identical orbits, moving at the same speed, the probability was effectively 0. Another group from the European Southern Observatory suggested the objects might be asteroids captured from another star system. As Alpha Centauri passed through a cloud of asteroids in the galaxy, some could have been gravitationally captured. But this hypothesis had its own problems. How could 3 objects from a random source end up on perfectly identical orbits? The odds of that happening naturally were far lower than winning the lottery. A theoretical physicist from Caltech even proposed a wild idea, that this could be a large-scale quantum phenomenon, with the three objects existing in a state of quantum entanglement, behaving as a single system. The idea was quickly dismissed. Quantum entanglement only occurs at microscopic scales, among tiny particles. No one had ever observed it in objects this large. In the end, after a year of debate, the scientific community was forced to accept an uncomfortable truth. They had no explanation. "I've worked in this field for 30 years, said an elderly professor from Cambridge in an interview. "I've seen many strange phenomena. But this is the first time I'm completely baffled. No natural model fits." "So what do you think it is?" the reporter asked. He was silent for a long moment. "I hesitate to say. Because the only explanation left is one that a scientist should not offer without overwhelming evidence. Can you give us a hint?" He looked directly into the camera. Three objects with identical orbits, perfectly precise, rotating opposite to everything natural in the system. If I saw this in a human-made engineering system, I would say it was intentional design. But this is space, he added quickly. I'm not saying it's artificial. I'm only saying we don't understand it yet. There may be a natural process we haven't discovered. The interview went viral. Headlines exploded across the media. Top scientist suggests intentional design at Alpha Centauri. Three mysterious objects, natural or artificial. Are we seeing the work of another civilization? Yang was forced to hold a press conference to clarify. We are not saying this is artificial, he emphasized. We are saying this is an unexplained phenomenon. Science needs time to find answers. But deep down, he wasn't sure. He spent sleepless nights running model after model, searching for any way to explain those three perfect orbits. There was none. Nature doesn't work like this. Nature produces chaos, randomness, variation. It does not produce three identical objects moving on flawless retrograde orbits, opposite to everything else. Unless there was something they hadn't accounted for. Some unknown force. Some new physical phenomenon. Or, a thought he barely dared to entertain, something not natural at all. While the debate over the three mysterious objects was still far from settled, another research team uncovered yet another anomaly in the Alpha Centauri system. Dr. Sofia Petrov of the Moscow Institute of Astronomy spent 2 years precisely measuring the temperatures of Alpha Centauri A and B. In theory, the task was straightforward: analyze the star's light spectra and compare them with established stellar models. But the results did not line up. According to stellar evolution theory, Petrov explained at a conference in February, a star around 5 billion years old like Alpha Centauri A should have a surface temperature of roughly 5,700 Kelvin. Alpha Centauri B, being slightly smaller, should be closer to 5,200. She pointed to a chart on the screen. But our measurements show Alpha Centauri A at about 5,900 Kelvin, and B at roughly 5,350. A difference of 200 degrees, someone remarked. That doesn't sound like much. In stellar physics, 200 degrees is enormous, Petrov replied. It's far beyond what measurement error can explain. We've checked repeatedly, using different instruments. The results don't change. Could it be metallicity? Someone suggested. Petrov shook her head. We checked that too. The metallic composition of Alpha Centauri A and B is nearly identical to the Sun's. There's nothing unusual there that would explain higher temperatures. Different ages, maybe? No, Petrov said. All three stars in the system, A, B, and Proxima, formed at the same time from the same gas cloud. They should be the same age. The room fell silent. Everyone understood what this implied: there had to be an additional source of energy that existing models failed to account for. Where could that extra energy be coming from? A professor from Yale asked. Petrov outlined several possibilities. First, tidal interactions between the two stars. Alpha Centauri A and B orbit each other at relatively close distances. Their mutual gravity could generate internal friction, producing extra heat. She moved to the next slide. Second, accretion. The stars may be absorbing material from their surroundings, dust, gas, small asteroids. As this material falls into the stars, it releases energy. Third, stronger magnetic fields than predicted. Intense magnetic activity can create hot regions on the stellar surface, raising the average temperature. And fourth, she paused, a process we don't yet understand. A physicist from Stanford stood up. Have you calculated how much extra energy would be needed to produce a 200-degree difference? We have, Petrov nodded. About 1,000th of the star's total energy output. That sounds small, but in absolute terms, it's enormous. Equivalent to how much? Petrov checked her notes. Roughly 10 to the 24 watts. In other words, about 1 billion times the total energy Earth receives from the Sun. The number silenced the room. 1 billion times. That was an immense amount of energy, and it had to come from somewhere. Of all the hypotheses you've mentioned, the Stanford physicist continued, which one do you find most convincing? Petrov thought for a moment. Probably a combination. Some from tidal interactions. Some from accretion. Some from magnetic effects. Together, they might be enough to explain it. But, she added, we need more data to be sure. Longer observations, more detailed measurements. This temperature anomaly, while not as dramatic as some of the other discoveries, was still significant. It suggested that even the main stars of the system, objects scientists believed they understood well, still held deep mysteries. With every new finding, the picture grew more complicated. An unusual atmosphere on Proxima b, repeating thermal signals. Radio emissions. 3 objects orbiting in reverse. A dust disk around an old star. Stellar temperatures higher than predicted. Each anomaly, on its own, might be explainable. But all of them together. All within the same star system. The odds that all these irregularities could occur naturally, by chance, in a single system just 4 light-years away, were extremely low. That is why the next discovery, involving a radio signal, would ignite the fiercest debate of all. Because this time, there was no easy way to dismiss it, this was a signal that nature finds very hard to produce. In March of 2020, Dr. Robert Chen of the SETI Institute decided to make public a dataset he had kept confidential for the past 2 years. Not because he wanted attention, but because he believed the time had come for the global scientific community to know. The press conference was held at SETI headquarters in Mountain View, California. The room was packed with reporters, not only from science magazines, but also from CNN, the BBC, NHK, and Al Jazeera. Everyone had heard the rumors that SETI was about to announce something big. Chen stepped up to the podium and adjusted the microphone. His hands trembled slightly. Since 2016, he began, after the discovery of Proxima Centauri b, the SETI Institute has devoted a significant portion of our observing time to listening for signals coming from the direction of Alpha Centauri. He paused and took a sip of water. We monitored many different frequencies. But one of our primary targets was 1420 MHz. Anyone familiar with SETI immediately understood the implication. 1420 MHz, the frequency of hydrogen, the most abundant element in the universe. Within the search for extraterrestrial life, this is often called the water hole. Why this frequency? Because if any civilization wanted to draw the attention of others, they would choose a frequency everyone knows. Hydrogen, with its natural emission line, is the most obvious choice. Like an unspoken cosmic agreement, if you want to communicate, use this frequency. Over the past 9 years, Chen continued, we have detected signals from the direction of Alpha Centauri at this frequency multiple times. A murmur rippled through the room. In total, he said clearly, 17 times. Chen advanced to the next slide, a timeline chart. The signal does not appear continuously. It shows up, lasts for about 10 to 20 minutes, then disappears. Sometimes months go by with nothing. Then it comes back. He pointed to the markers on the chart. The first time, June 2018. The second, December of the same year. In 2019, nothing. In 2020, 3 times. In 2021, once. In 2022, none. In 2023, 4 times. In 2024, 5 times. And so far in 2025, 3 times. Is there any pattern? A reporter asked. Chen shook his head. We've looked for one. Nothing obvious. But there is something interesting. He brought up a new slide, a frequency spectrum. This signal is extremely narrow. About 5 Hz wide. In nature, most radio sources, stars, galaxies, nebulae, emit across thousands or millions of hertz. A signal this narrow usually comes from a transmitter with intent. Like a radio station, someone said. Exactly, Chen nodded. Just like radio stations on Earth. They concentrate energy into a narrow band to transmit information efficiently. A reporter raised a hand. Are you saying this is an artificial signal? Chen exhaled slowly. That's the question I've wrestled with for 9 years. And honestly, I don't know. But what do you think? Personally. Chen looked straight into the camera. I've worked in this field for 30 years. I've heard thousands of strange signals. 99% turn out to be interference from satellites, aircraft, or equipment errors. But the remaining 1%, he continued, are signals we can't explain. Most appear once and never return. We can't confirm them. This one is different. It comes back. 17 times in 9 years. That's not random. So what do you think it is? Chen was silent for a long moment. There are 3 possibilities. 1. This is a natural phenomenon we don't yet understand, perhaps related to Proxima Centauri's magnetic field, or interactions between the star and its planet. 2. It's interference from Earth that we somehow haven't been able to trace. 3. He paused, it's an intentional signal from a non-natural source. The room erupted. Reporters shouted. Cameras flashed. Questions flew from every direction. Chen raised his hand. I want to be clear. We are not claiming this is a signal from extraterrestrial intelligence. We need more data. Independent confirmation from other observatories. We need to rule out every possible source of interference. But, he added, we also can't ignore it. A repeating signal, at a special frequency, coming from the direction of the nearest potentially habitable planet, this is exactly what SETI was created to look for. In the following week, radio observatories around the world turned their antennas toward Alpha Centauri. Everyone wanted to verify the signal. The results were inconsistent. Some detected similar signals. Some saw nothing at all. Others picked up signals, but at slightly different frequencies. The inconsistency made everything more complicated. If this was a real signal from Alpha Centauri, why didn't every observatory detect it? If it was interference from Earth, why did it keep coming from the same direction? One hypothesis emerged. The signal wasn't continuous. It transmitted only at specific times. If an observatory wasn't looking at the right moment, it would miss it entirely. But why would the signal be intermittent? If it were natural, like radiation from a star, it should be continuous. If it were intentional, why transmit only occasionally? An astronomer from Australia proposed an intriguing idea. The source could be on the surface of Proxima b. As the planet rotates, sometimes the transmitter faces Earth, sometimes it turns away. That would explain the irregular appearances. The idea made sense. But to test it, they needed the planet's rotation period, which they already knew, 11.2 hours. A research team analyzed the timing of the detections. If the hypothesis were correct, the signals should be separated by exactly 11.2 hours, or multiples of it. The results were inconclusive. Some pairs matched the period perfectly. Others didn't. It could have been due to incomplete data. Or a moving source on the planet's surface. Or the hypothesis could simply be wrong. The debate dragged on for months. No one had a definitive answer. Then a physicist from MIT raised an important point. No matter what the source is, we need to remember that Alpha Centauri is 4.37 light-years away. The signal we're receiving today was actually transmitted about 4.5 years ago. If this is an intentional signal, he continued, it was sent in 2020. Before Webb detected Proxima B's atmosphere. Before we knew anything remarkable about this planet. What does that mean? Someone asked. It means that if someone out there is transmitting, he said, they're not reacting to our discoveries. They sent the signal earlier. They may have been transmitting for years, even decades, and we only just started listening. That idea, that someone might have been calling out to us for decades while we weren't paying attention, unsettled many people. SETI has been operating for over 60 years, scanning the skies for signals. They focused on distant stars, on galaxies at the edge of the universe. Meanwhile, the nearest planet, just a few light-years away, may have been transmitting all along. We weren't listening because we thought it was too close, too ordinary, nothing special. Now, everything has changed. While the world focused on the radio signal, Dr. Rachel Martinez and her atmospheric chemistry team spent an entire year dissecting the composition of Proxima B's atmosphere in painstaking detail. They did not just want to know which gases were present. They wanted exact concentrations. They wanted to understand the chemical reactions taking place. They wanted to calculate how long each gas could survive. In April 2020, they published their findings in a paper more than 100 pages long in Science. The key results were clear. Oxygen in the atmosphere was measured at about 400 parts per million, with an uncertainty of plus or minus 20 parts per million. Methane came in at roughly 2 parts per million, with an uncertainty of plus or minus 0.3. These are the most precise measurements ever made of an exoplanet atmosphere, Martinez wrote in the introduction. They are based on 30 separate observations from Webb, combined with additional data from ground-based telescopes. But the most important part was not the measurements themselves. It was what came next. Martinez and her team built a detailed chemical model of Proxima B's atmosphere. They calculated how fast oxygen reacts with methane. They modeled every possible source that could produce these gases. They calculated how long the gases could last. The final result appeared in a simple table, and it was shocking. With an oxygen concentration of 400 parts per million and methane at 2 parts per million, Martinez wrote, at an average temperature of 280 Kelvin, about 7 degrees Celsius, and a pressure of 1 atmosphere, the time it takes for oxygen and methane to completely react with each other is. She paused, checked the math for the 10th time. About 100 years. 100 years sounds like a long time. But compared to the age of a planet, 4 billion years, it is the blink of an eye. This means, Martinez explained in an interview, that oxygen and methane in Proxima B's atmosphere cannot exist naturally. They should have reacted away long ago. But they are still there, the interviewer said. Exactly. Which means something must be continuously replenishing them. A process powerful enough to produce oxygen and methane faster than they destroy each other. What process is that? Martinez shook her head. That is the question we have spent the past year trying to answer. We examined every natural possibility. She walked through the hypotheses they tested. Volcanoes could produce both oxygen and methane, but sustaining the observed levels would require millions of volcanoes erupting constantly. Webb's data showed no evidence of volcanic activity anywhere near that extreme. Photochemical reactions could split water into oxygen and hydrogen under starlight, but this process does not produce methane. In fact, it destroys methane. Geochemical reactions in oceans could release gases through mineral interactions, but the production rates were far too slow to replace what chemical reactions would remove. Asteroid impacts could release gases from the planet's interior, but maintaining stable levels for millions of years would require an unusually high and constant impact rate. Every hypothesis has a problem, Martinez concluded. No known geochemical process is strong enough to explain what we see. So what's left? Martinez was silent for a moment. What's left is biology. On Earth, she explained, we have oxygen in our atmosphere because of plants. They perform photosynthesis, using sunlight to split water into oxygen and hydrogen, releasing oxygen into the air. And we have methane because of microbes. They live in swamps, in animal guts, in the oceans. They produce methane as a byproduct of their metabolism. These two processes, oxygenic photosynthesis and methane-producing fermentation, are biological. They are powerful. They can generate enough gas to keep an atmosphere in balance. Are you saying Proxima b has life? The interviewer asked directly. I am saying, Martinez chose her words carefully, that the chemical data we observe are consistent with a biological hypothesis. It does not prove life exists. But it also does not rule it out. To be confident, she continued, we need to find additional biosignature gases, gases that only life produces in significant amounts. Like what? Phosphine, Martinez replied. A toxic gas that on Earth is produced only by anaerobic bacteria. If we detect phosphine in Proxima b's atmosphere, that would be strong evidence for biology. Dimethyl sulfide, produced by marine algae. Ammonia at high concentrations. Nitrous oxide, created by soil bacteria. Any one of these gases, if detected at sufficiently high levels, would be very difficult to explain without life. Have you looked for them? Martinez nodded. We spent 60 hours of Webb observation time searching for these gases. The instrument sensitivity is just enough to detect them if they exist at levels similar to pre-industrial Earth. And the result? Martinez smiled wearily. We detected, maybe, a weak signal that could be phosphine. But it sits right at the noise threshold. We need more data to be sure. How long will that take? Webb has granted us another 100 hours of observation next year. If the signal is real, we will confirm it. And if it is real? Martinez looked straight into the camera. If it is real, if we confirm phosphine in Proxima b's atmosphere, combined with oxygen, methane, water vapor, and all the other evidence, then for the first time in history, we will have solid evidence of life beyond Earth. Not fossil microbes on Mars. Not organic molecules in meteorites. But a living, active biosphere, just 4.5 light-years away. The interview spread around the world. Headlines appeared everywhere. NASA scientist, we may confirm alien life within a year. Proxima b, chemical evidence points in one direction. Are we alone? The answer may be coming soon. Pressure on Webb doubled overnight. Every research institute wanted observation time. Everyone wanted to confirm, or refute, the discovery before someone else did. Never before in history had a scientific question captured the attention of the entire world like this. Are we alone in the universe? The answer, whether yes or no, will completely change how humanity sees itself. May 2020. The International Space Agency convened an extraordinary conference in Geneva. This was not a routine scientific meeting. It was an emergency gathering of the world's leading scientific leaders from 50 countries. The goal was simple, and monumental, to assess all available evidence about Proxima Centauri b, and to decide what humanity should do next. Sarah sat in the vast auditorium, scanning familiar faces. Chen from SETI. Martinez from NASA. Yang from Hawaii. Park from Signal Analysis. Foster from Cambridge. Wong from Tokyo. Petrov from Moscow. Rivera from Arizona. All of them had devoted years of their lives to studying this star system. All of them had uncovered different pieces of the puzzle. Now, it was time to put them together. The director of the European Space Agency stepped forward and activated the massive projection screen. Let's review everything we've discovered over the past 2 years. A list appeared on the screen. First, Proxima Centauri b possesses a dense, multi-layered atmosphere, something that should not exist around a violent red dwarf star. Second, the planet has an extraordinarily strong magnetic field, 5 to 7 times stronger than Earth's, powerful enough to shield its atmosphere from radiation. Third, the atmosphere contains oxygen and methane coexisting together, an unstable chemical combination that requires continuous replenishment. Fourth, repeating thermal signals with astonishing precision, perfectly synchronized with the planet's rotation, unlike any known natural phenomenon. Fifth, radio signals at 1420 MHz, the exact frequency SETI has searched for over 60 years, detected 17 times across 9 years. Sixth, 3 objects orbiting Alpha Centauri A in reverse direction with identical trajectories, a configuration with an almost zero probability of occurring naturally. Seventh, a dust disk surrounding an old star, with temperatures far higher than expected. Eighth, Alpha Centauri A and B exhibiting higher temperatures than theoretical models predict, suggesting an unexplained additional energy source. Ninth, a long-lasting chemical imbalance, oxygen at 400 parts per million, methane at 2 parts per million, despite a theoretical atmospheric lifetime of only 100 years. 10th, faint signs that may indicate phosphine, a potential biological gas. Each discovery on its own, the director said, can be explained. It could be coincidence. It could be a rare natural phenomenon. He paused, scanning the room. But all of them together. In the same star system. The closest star system to Earth. No one answered. Because everyone already knew. The probability that all these anomalies could occur naturally, randomly, within a single star system was unimaginably low. A professor from Oxford University stood up. We are facing 2 possibilities. Only 2. He raised one finger. First, everything we think we know about planet formation, atmospheric chemistry, stellar physics, orbital dynamics, all of it is wrong or incomplete. We would need to rewrite the textbooks from scratch. He raised a second finger. Second, we are seeing signs of life. Not just simple microbial life, but possibly complex life, possibly intelligent life. Both possibilities are extraordinary, he continued. Both would fundamentally transform science. But we must choose one. Sarah stood. I'd like to speak. For the past 2 years, I've been the most cautious voice in this room. I warned against jumping to conclusions. I warned against letting imagination outrun evidence. She looked around the hall. But now, after examining all the data, after eliminating every natural explanation one by one, I have to admit that we are facing an unavoidable possibility. Proxima b may host life. The words hung in the air. Not certainty, she quickly added. We still need to confirm phosphine. We still need to explain the thermal signals, the radio signals, the 3 retrograde objects. But every piece of the puzzle points in the same direction. If we refuse to consider this possibility simply because it is extraordinary, then we are no longer scientists. We become dogmatists. Chen from SETI rose to his feet. I agree with Dr. Sarah. For 30 years, SETI searched for signals from stars hundreds, thousands of light years away. We found nothing. Now, he continued, at the nearest star, just 4.37 light years away, we're not seeing one anomaly, but 10. If this isn't a signal demanding our attention, then what is? Martinez spoke next. Within 1 year, we'll have results on phosphine. If confirmed, it would be the strongest chemical evidence for biology ever observed. Combined with oxygen, methane, a powerful magnetic field, a stable atmosphere, it would be extremely difficult to dismiss. But, a skeptical voice from the corner of the room objected, what if we announce life, and later discover we were wrong? The credibility of science would be shattered. And what if we have evidence and still refuse to acknowledge it? Another voice shot back. That isn't science. That's fear. The debate lasted 3 days. 3 intense, exhausting days. Not over the data was clear. But over meaning. Responsibility. And what humanity should do with this knowledge. In the end, a consensus was reached. On May 23, 2020, a joint statement was released from Geneva. After reviewing all available evidence from the James Webb Space Telescope, global radio observatories, and ground-based optical observations, the international scientific community concludes the following. First, Proxima Centauri b possesses a planetary environment unlike any world we have ever observed. Second, the chemical characteristics of its atmosphere, combined with an unusually strong magnetic field, suggest processes that may be biological in nature. Third, multiple unexplained signals, including repeating thermal patterns, radio emissions at 1420 MHz, and orbital anomalies within the system, require further investigation. Fourth, within the next 12 months, additional observations will be conducted to confirm or refute the presence of phosphine and other biological gases. Fifth, if phosphine is confirmed, it will represent the strongest evidence for extraterrestrial life ever discovered. Sixth, regardless of the outcome, Proxima Centauri b will become the highest priority target for exploration missions over the next decade. The statement ended with a sentence that made the world hold its breath. For the first time in human history, the question, "Are we alone?" is no longer philosophical. It has become experimental science. The answer lies within reach, just 4.37 light-years away. Within 6 months of the announcement, everything changed. NASA unveiled plans to build a probe to Proxima b. Not decades from now. Within 10 years. Using technologies never deployed before, light-driven propulsion, laser sails, even antimatter engines if possible. We can send a small spacecraft at 20% the speed of light, the NASA administrator declared. It would reach the system in 22 years. 22 years from now is still within humanity's most active scientific era. The European Space Agency announced a project to construct a massive radio telescope array on the far side of the Moon, shielded from Earth's interference, capable of listening to Proxima b 24 hours a day. China declared plans to upgrade FAST, the world's largest radio telescope, to focus entirely on Alpha Centauri. Japan, India, Brazil, South Africa, all announced their own initiatives. All aimed at the same target. For the first time in history, humanity united around a single goal, to uncover the truth about Proxima b. In classrooms around the world, teachers told their students, "In your lifetime, we may know the answer. Some of you may be the ones who discover it." In churches, temples, and mosques, religious leaders debated the theological implications. If life exists elsewhere, does it change belief? In government chambers, politicians discussed policy. If intelligent life is confirmed, should we reach out? Or remain silent? Yet amid the chaos, the excitement, the fear, there was one simple truth everyone agreed on. We had changed. No matter what the final answer turned out to be, we were no longer the same species we had been 2 years earlier. We had looked outward. We had searched. We had found something. Maybe life. Maybe the strangest natural phenomenon ever discovered. But whatever it was, it had forever changed how we see the universe. Sarah stood on the Institute's rooftop on a June night, gazing up at the sky. Her eyes searched for a familiar star, Alpha Centauri. Brilliant. So close it almost felt within reach. She thought about Proxima b. A planet locked in eternal twilight. It might have small oceans. It might have gentle winds flowing from the dayside to the nightside. It might have life. She thought about the signal. 17 times over 9 years. Was someone trying to call out, or was nature speaking in a language we have not yet learned to understand? Next year, they would know more about phosphine. The year after that, perhaps they would confirm other biosignature gases. 10 years from now, the first probe might be launched. Within her lifetime, maybe, just maybe, humanity would finally have an answer to the oldest question of all, are we alone? Her phone rang. Martinez. Sarah, you need to see the latest Webb data. Right now. What's going on? Phosphine, Martinez said, his voice trembling. We just confirmed it. The concentration is higher than we expected. Much higher. Sarah felt her heart pound. Are you sure? We checked 5 times. There's no doubt anymore. Proxima b has phosphine in its atmosphere, in amounts that only biological processes can explain. Sarah looked back up at the sky. Alpha Centauri was still shining there, just like every other night. But now, everything felt different. We need to go public, she said. I know, Martinez replied. The press conference is next week. This time there's no maybe. This time we say it clearly, we have found it. The call ended. Sarah remained where she was, staring at the star. 4.37 light-years away. In cosmic terms, it was right next door. With today's human technology, it was still an immense distance. But not an impossible one. The previous generation put humans on the moon in 10 years. Maybe this generation would send humans to another star. Maybe the children born today would grow up to see the first images from the surface of Proxima b. To know for sure whether life exists there. To meet, or not meet, our neighbors. The story of Alpha Centauri was only just beginning.